Hi everyone, I am Abhinav and today we will be discussing the third problem from the CP-31 sheet by TLE Eliminators under the 1500 rated questions. Okay, so we'll move to the CP-31 sheet and we can see that the 1500 rating mark has been checked. We can see the clickable links for our problems. So let's click on this third problem, which is block sequence. Okay, let's read the problem statement. Given a sequence of integers a of length n, a sequence is called beautiful if it has the form of a series of blocks, each starting with its length, that is, first comes the length of the block and then its elements. For example, this sequence, this is beautiful because you can see here there is a 3, then there are 3 elements. Okay, so this is a single sequence. Okay, a 3 and then 3 elements. This is a single sequence, and then a 2 and then 2 elements. This is a single sequence. So this entire array can be broken down into these two sequences. Okay, so we can say that this particular sequence, basically it can be broken down into blocks. Okay, is called beautiful if it has the form of a series of blocks, each starting with its length. So this is one block starting with a length 3 and then 3 elements. This is another block starting with a length 2 and then 2 elements, 2 more elements. So we can see that this sequence can be broken down into these 2 blocks of this type. Then this is a beautiful sequence. Same way for this is a single block of 1 then 1 element, a 4 then 4 elements. So this is a single block, this is a single block. This sequence can be broken down into 2 blocks like this. So this is also a beautiful sequence. That's the definition of a beautiful sequence. We can look, these sequences are not beautiful because you can see there's a 1 and then there are no elements. So this cannot be broken down into blocks starting with the length of the block and then there's many elements, because there's a 1 and then there are 0 elements. Here you can see there's a 1. So if we consider this 4 inside this block, so this would form a single block, a 1 and then 1 element. But again, there's a 3 and then there are no elements. There should be 3 more elements after this to be a good sequence. Same way, there's a 3 and then there are only 2 elements. There should be 1 more element for this to be a good sequence. Okay, so you can see these are not good sequences. In one operation, you can remove any element from the sequence. What is the minimum number of operations required to make the given sequence beautiful? So basically, you are given some sequence, you need to make this sequence beautiful by removing some elements. Okay, and you need to find the minimum number of operations, basically minimum number of removals, so that this sequence becomes a beautiful sequence. That's our problem. You can see the constraints of the problem. Okay, let's take this first test case and understand what we need to do. Okay, like in the first test case, you can see like for this test case, you can see there's a 3 and then 3 elements. So these 4 elements form a single block, and then there's a 2 and then 2 elements. So these 4 form another block. Okay, so this is already a good sequence. You can see this is already a good sequence. So 0 number of removals are required. No removals in this sequence is required. The minimum number of removals required is 0. So this is already a good sequence with 0 removals. Answer for this is 0. Now if you see the second test case, here you can see in this sequence there's a 4, there's a 5, and then there are only 3 elements. So in order to for this sequence to be beautiful, with a 5 there should be like 2 more elements. Now since we cannot add elements to the sequence, we can only remove elements. So maybe we can remove this 5. Okay, then again with this 6 there should be 6 more elements which are not there. So maybe we'll try to remove this 6 also. Now with this 3 there should be 3 more element which is not present. We'll remove this 3 also. With this 2 there should be 2 more elements, nothing is there. So what we can do in this array is just remove all the 4 elements, we get an empty sequence. Now this empty sequence would be beautiful. Okay, this empty sequence would always be beautiful because there are no elements, nothing there. So an empty is always beautiful. So for this, the best thing we can do is just remove all the 4 elements and then make it an empty sequence which is beautiful. So our best answer would be 4 removals, because if we leave any element there, we cannot make it a good sequence. Okay, just try, you can just try. Even if you leave a 2, then you need to have 2 more elements to the right of that which you don't have. Okay, so in this particular, our answer is 4. Just remove all the 4 elements. Okay, if we look at the third test case, okay, here our answer was 4. You can look. Now, if we look at the third test case, here you can see this was our sequence. Now, for it to be a good sequence, if you have a 3 and 3 more elements, so this, all these 4 would form a single block. Okay, these 4 would form a single block, no problem. Now with this 7, we don't have 7 elements, so what we can do, we can remove these 2 elements from this. So these 4 form a single block. Now we only have if we have only these 4 elements, it would become a good sequence, or a beautiful sequence, you can say. It would become a beautiful sequence if we remove these 2 elements. So answer this for this would be 2. If we remove 2 elements, we can make it a good sequence. This was one possible case for this. Another way of what was another way to do it is, okay, one way was remove this 7 and 7. This would be a good sequence. Now another way I am telling is, if we remove this 3, then we have a 4 and 4 more elements in front of this. So in this case, this whole, all these 5 elements became a single block with this length 4 and then 4 more elements. So this became a single block. So just by removing 1 3, we are able to make it beautiful. So our answer would be 1 here. Just removing this one element 3, we can make it beautiful. So the minimum number of operations would be 1. One way was to make it beautiful by removing these 7 in 2 operations. Another way was make it beautiful by removing this 3 in 1 operation. So what's the minimum? 1 is the minimum, so our final answer would be 1. You can see for this third test case, our final answer was 1. Okay, so I hope you understood the problem. What we need to do is, we need to find in minimum number of operations, how can we make this array, make any array beautiful. Now, what's the problem here? The problem is, like in this test case, you saw one way was is remove these 2 elements, make it beautiful by 2 removals. Another way was remove this element, make it beautiful with just 1 removal. But how would we find which all elements should we remove to make it beautiful? Okay, so this was a little problematic thing. Okay, so like, let's try to first, let's see the constraints and just decide what time complexity and all would be acceptable here. So if we look, n is up to 2 into 10 to the power 5 and ai is up till 10 to the power 6. So if we have n up to 2 into 10 to the power 5, what does that mean? If we apply some logic which is going O of n square, that would take 4 into 10 to the power 10 operations, which would be way more than 10 to the power 8 operations that we can do in 1 second. So I think you can understand that O of n square would not work here. We need to do something better than this. So what you can do is, if we the expected time complexity, either you can do in something like order of n, 2 into 10 to the power 5 would be very fine, or you can also go in something of n log n type complexity also, or maybe also n root n would also be accepted, and root n is approx 10 to the power 7 to 10 to the power 8 only, so that would also be accepted. If you can get some logic where there's n root n, that would also be fine for this problem. But majorly we get some complexities like n or n log n or n log n square. Those complexities would be accepted here, so that you can understand by reading the constraints of the problem. These would be our expected time complexities. Okay, now let's look at this problem and find some logic how we can do in some order of n time. Okay, now what was the problem here? Here the problem was, we can just remove any element. If we remove this 3, we get something like this. From 4, then 4 elements. Okay, now, but since you saw even removing this 3 was not required, because with this 3 you get 3 more elements, so this was forming a good block. So this, removing this 3 was not logical at the start. If you see, then removing these 7s was the first thing that you got by looking at this test case, that remove these 2 7. But a better way was remove this 3, so that you get a 4 at the start and you can cover all these 4 elements inside this block. Okay, so what can we do here? How can we find out that which one should we remove? Okay, so you can look like we tried to doing something greedily, like if we just look at this three, then skip the three elements, remove them, but that was not working. Now if we try to remove this three and then, but still, like, there would be many other cases also. Maybe removing this 4 in the middle somewhere was something beneficial, or something else was beneficial. So a greedy type of approach is not working, but we know here that we need to either keep an element or remove an element. This intuition you would have got, that you need to minimize the number of removals. So basically at the end, what would happen, every element, every index I can have either two states. Either this would be present in my final answer, best answer, or it would be absent there, it would be removed. Every element, either it would be present or it would be removed, either present or removed. These can be the two cases. So all those elements that are present, among them you should form a good sequence. That's your question. And if you minimize the number of removals, that means the number of elements that are present in your final sequence, that is maximized. So what you can do is, you can try something dynamic programming approach, because you know every element has two states, either remove it or not remove it. So one way to do it is just do a brute force through recursion. Just go one by one. Just one time remove this element and one time not remove this element. So when you reach the final array, then just check whether that is a beautiful or not. If that is beautiful, the number of removals that you can manage and minimize. So if you are going on a recursion, one time you are removing it, one time not removing it, that way if you are going, that would, the recursion would take a complexity of 2 to the power n, because from at the first state you would have a state, let's say, like for this case I'm defining the indexes as, okay, let's say we have zero based indexes only. So initially you would start with the index 0, and then there would be two ways, either remove this index 0 or keep this index 0. Okay, so remove, I'm representing with 0 or 1. So if you are removing it, you would have an empty array when you would go to I equal to 1, and if you take it, you would have an array with 3 present when you go to I equal to 1. Now again you would have two cases, either remove it or take it, this I equal to 1 index. So if you take it in this case, you would have 4. If you do, like, if you don't take it in this case, you would have again an empty array, and if you take it, you would have a 4. In this test case, if you don't take it, you would have a 3 left, and if you take it, you would have 3 comma 4 left. Then you would go to I equal to 2 case. So that way you can see, initially there was only one state, then two states, then four states. So we are going exponentially, you can understand, in 2 to the power n. There would be 2 to the power n states in total. If you are doing it through recursion, either take it or not take it if you are applying this logic. But if you have studied about dynamic programming, you would know that this type of recursion, which is taking 2 to the power n time, that can be reduced to order of n time by using a DP. How you can do it is, basically there would be a lot of times when some states are repeating. So you can optimize that thing by storing the states in some DP array. So I hope you would have got the intuition why we are going to use DP here. So for DP you would need a state and a transition to keep. So what state should we take for our DP? Okay, so whenever we are at the ith index, what we can do is take the state that if you are at this ith index, then what you need to do is you need to go forward, and for the remaining, you need to make them beautiful basically. So what DP state I am going to take is, my DPI is going to represent, I can take a DP state where my DPI is going to represent that, like, since in general, when we take a DP state I, we take this array. Okay, if we have went till I, we are going from the left, then we have taken this sub array, we calculate our answer for this sub array. That's what the, like, in most of the question, when we take a DP state, our DP state in general, the first thing we think is represent our answer through the DP state. Here our answer is minimum number of removals to get a beautiful sequence. So if we take a DPI, that should represent the minimum number of removals to get a good sequence for the subarray from 0 to I. But since here you can know that for a sequence to be beautiful, if this is a 3, there should be 3 more elements ahead of this. If this is a 4, there should be 4 more elements ahead of this. So the so if you have some subarray like this and you are moving this side, then basically, you know, if this is a 3, you would need to have 3 elements, but that can be any elements. So instead of taking it in this direction, if you are taking the state in this direction, that would be more beneficial, because you know this is your first element for sure. Then you would need one more element. Okay, then if this is your next starting element, for sure you would need 7 more elements. So you can analyze better by taking it in this direction. So I am taking the DP state as like this, that my DPI represents that for sub array from I up till n. Okay, I'm taking it for the writer subarray, for the subarray starting with I and ending with n. So we'll in the DP we'll be moving in this direction, not in that direction. Okay, so okay, why I took it, I'll explain when I'll be writing the transition, because you take the state based on whether you can write the transition for that or not. Okay, whenever you use a DP, keep that in mind. You take a state such that you can write a transition for that state. If you can't write a transition for that state, you cannot solve the problem. So if you take a DP from this direction or this direction, okay, that you would take based on the transition. Okay, so if I'm taking it like this, when I'll come to transition, I'll show you how I can write the transition if I'm taking it like this. So that means for the subarray from I to n, what's my answer? That's what the DP state. And what's my answer? That means the minimum number of operations to make the, basically this subarray, this sequence, make the subarray beautiful. Okay, this is my DP state, you can say. This is my DP state, that my DPI represents that if I have an array like this and here somewhere is my DPI. My DPI represents that for this subarray, if you only have this subarray as a question, then what's my answer? If you only have this subarray, then what's the minimum number of removals from that, so that I can make this sequence beautiful? That's my DP state. Now how can I write my transition? Okay, so if this is I, this is I minus 1, the element just before that. Or you can say if this is I, the element just next to it is I plus 1. So always in my transition, either I would write DPI in terms of DPI minus 1 or DPI in terms of DPI plus 1. If I can represent it like this, then I can write my transition. So what I can say is, if I have this ith elements, I would have two choices, either take it or remove it. So let's write the transition for both the cases. So I'm writing my transition. If I have a DPI, so one way is if we remove it. Okay, so if I'm removing this ith element, that means for this whole to be beautiful, if I'm not taking it, that means this whole should be beautiful. What's the minimum number of operations to make this whole subarray beautiful? Would be same as if I'm removing this element and then making this whole beautiful. Okay, so if I remove this and then I would need to make this beautiful. So by removing this is taking one operation. So I can write this as one operation for removal and then DP of I plus 1. That is one way if I am removing it. If I am removing the ith element, that means the minimum number of operations to make this whole thing beautiful plus 1 would be the minimum number of operations to make this beautiful by removing it. And if I don't remove it, then what would happen? If let's suppose at this ith index I have a 3, okay, the value at this is 3. So if I'm not removing it, that means for this sequence, if this is not removed, this would be the first element of the sequence for sure, because you don't have anything to the left. You are starting your sequence from here. That means this would be the first element and this is coming for sure. So if this 3 is there, then we would have 3 more elements after this. Okay, so these 4 elements should be there to make it a beautiful block. And after that, after the 3 elements, the remaining array should be beautiful. Basically what I'm telling is, you have this single block and then make the remaining beautiful. Okay, you know this block is okay, this block is beautiful, no need to remove anything, make the remaining beautiful. If you are removing something from here, that means you are just extending here 1 2 elements more you are taking and then making the remaining beautiful. That whole process would be covered if you are if you are supposing that the next 3 elements are taken. If any one of them is not taking, then in this you are considering all the cases where you are not taking this, not taking this, and this is covered. Okay, so this way all the cases would be covered. If so, from which index I'm telling is, if there is a 3 or at the value at this is ai, okay, so then take 3 elements here. Okay, so what would be the index of the next after those 3 elements? What would be this index? This is I, then I plus 1, I plus 2, I plus 3. This would be I plus 4. So how we got I plus 4 is I plus AI. AI was 3, then plus 1. Okay. So if AI was 1, we would have I plus 1. Then I plus 2 would be the element from where we have to make it beautiful. If ai is 3, it means I plus 1, I plus 2, I plus 3, and then from I plus 4 we need to make it beautiful. So from I plus ai plus 1, this would give you this index. From this index you have to make it beautiful. So we can write the state as, it would be same as making it beautiful from I plus ai plus 1. If you can make, what does this dp state represents? This dp state represent that minimum number of operations required to make this thing beautiful. So you don't need to delete any elements from these 4 elements, 3 and these 3 elements, these 4 are a complete block, you don't need to remove anything. So the number of removals would be only through this. So the dp of I plus ai plus 1, whatever the value of this is, this only would be the minimum number of operations for dpi also, if you are taking these elements. Okay, so my final answer would be either this or this, whichever is giving you the minimum, that would be your final answer. So I can write my transition like this: the minimum of 1 plus dpi plus 1, or this. Now it may happen that this I is, let's say for this, for some array, okay, there is some array, then there's a 3, let's say, and then 1 element, and it's the end of the array. Okay, so this is the n minus 1th index, this is the n minus 2th index. So when you are at this index and then you write I plus ai plus 1, so I is n minus 2 plus ai is 3, so this would give me n minus 2 plus 3 plus 1. This is giving you n plus 2. So if you are trying to find the dp of n plus 2, basically you are going, you need to have 3 elements here, you are going out of there. So you don't have 3 elements in front, still you are supposing that you are taking these 3 elements, so that is wrong. So you would have to have a check here that this thing should not exceed n. So this would only be valid when this thing doesn't, this I plus ai plus 1 doesn't exceed n. So if you have a 3 here, you should have at least 3 more elements here. So this I plus ai, that can be up to n minus 1. So I plus ai plus 1 can be up till n. So if we have 3 more elements here, then that is valid. So you would have n minus 1 here, n minus 2, n minus 3, n minus 4. So then we would have n minus 4 plus 3 plus 1, this I plus ai plus 1, which would be n. So this n is fine. N just represents that there is nothing ahead of this. Okay, even if you have n plus 1, if you get this as n plus 1, then that basically means you cannot have three more elements here. So that one extra check you would have to have if you are using this. If this thing is going, if this thing is greater than n, then you would only have this as the only state. You would not take min, you would have only this state, and you would take the minimum of this or this only when this thing is less than equal to n. Okay, so I hope you understood this extra case that you would have to check in your code while writing your transition. Okay, and so basically this is your transition. Now you would have got why we took our state like this, that dpi represents that for subarray from I to n. Why not from 0 to I? So if we had taken the subarray from 0 to I, then for that the transition we would have to write, for I we would have to write based on I minus 1. Now if you are not taking this and you have this array, like how can you confirm from this that this is beautiful if you are taking this or not taking this? That would, for this, if you're taking or not, that would represent somewhere in this, like uh, if you suppose, for this array only, let me just screen it. Okay, let's say if you're taking the, in a usual way, you're taking dpi as this subarray, then if you have to write the transition for this dpi, then you would have to write this on the basis of something to the left of I. So if you are taking this one or not taking this one, how would you be able to write the transition? That if you are here and there's a 3, that means you need to have 3 more elements. So how many elements more you need to have, that would be depend something to the left of this. So you would have to traverse one by one to every element to the left of this. So that writing the transition would only take something order of n or something greater than that time. We need to have a transition in order of 1. So that we were not able to write by taking it to the left. But since by taking the state as like this to the right, we were confirmed that if we are taking it, this is my first element, have one element after this and take the dp of that. If we are not taking this, then just take the dp of that. So from the question we can understand whether we need to take it from the left side or the right side. Okay, I hope you got what kind of transition or what kind of, how we decided what state we are taking, and basically the state is decided if we can write the transition or not. So I hope you understood the state and transition of the dp. One more thing that we need to write for writing a dp solution is the base case. Okay, so what would be our base case here? So you can understand I am writing my dpi depending on dp I plus 1. So my ith dp depends on I plus 1. So in order to start, so basically to for calculating our dp stage, I would have to move from the right to left. If my I plus 1 is calculated, then only I can calculate I. So I would have to move from the right to the left. So my base case would be at the rightmost. So my base case would be either the dp of, so what's the last dp? What is dp n minus 1? Or it can be dpn. So what does my dp n minus 1 represents? That for the subarray from n minus 1 is my last element. So for this subarray, what's my answer? And dpn represents that for the empty subarray, what's my answer? So you can see that for this case, you may have a dp of n also. When from I there are ai elements more, this block is entirely covered, then you take a dp of an empty array which is stored in dpn. So my base case is dpn, which represents an empty array. So for an empty array, I can say in 0 number of operations, we can make it beautiful. We know that an empty array is always beautiful, so we don't need to apply any operation on that. So my dpn represents an empty array, which would be 0. So this I can say is my base case, that dpn equal to 0 would be my base case I can write. Okay, so from that I would be able to calculate my dp n minus 1 when I'll move to dp n minus 1. One way would be 1 plus dp I plus 1. So 1 plus dp n would give me 1 here for the last element, and this thing always would be greater than n for n minus 1 case, because when you have, even at the end of the array, Even at the end of the array, if you have a 1, then if you are writing for this the DP with 1, you need to have one more element at least. So you can never make this thing, you can never make an array of one element beautiful, so we'd have to remove it. So my dp n minus 1 would always be 1. So instead of writing this as the base case, you could have also written dp n minus 1 equal to 1 as the base case. That would also be fine. Or you can just write this as the base case and start calculating from n minus 1. This would be computed while calculating a transition only. So both of the base cases would be fine in this case. Okay, I hope you understood the base case, the state, and the transition. So now we can move to our solution, move to our code. Once you have written these three things for a DP solution, you can very easily write your code. Okay, I hope you got the approach. So we'll move at the code. So what I did here is I just took, these are the input t test cases, then n, and then array of size n. These all input part is done. Okay, then what we would do is we initialize a dp array of size n plus 1 so that we have access to dp n also. So we wrote the base case. This was our base case, dp n equal to 0. You can see this was our base case. So we wrote this base case there. And then as I told you, I'm writing an iterative solution, so I would need to know from where we have to compute. So since my dp, you can understand from the transition that since my dpi is depending on dpi plus 1, so I would have to compute from the right to the left. So for computing I, my I plus 1 should be already computed. So I would have to move from right to left, from basically n minus 1 to 0. So I'll run a reverse loop from n minus 1 to 0, I minus minus. This way I would compute my dp. So whenever I am computing dpi, my dpi plus 1 is already computed. Now inside the loop I would write my transition. So my dpi, this thing would always exist, and for this we would have to check whether this is less than equal to n, then only. So I can directly write dpi as this, and then I'll take the minimum of that with this. If this thing is I plus ai plus 1 is less than equal to n, then we would just take the minimum of this and this, otherwise we'll leave it this only. So I initialize my dpi with dpi plus 1 plus 1. So this, the case where we are removing the ith index, that is what we are initializing my dp with. And then in j I am taking I plus ai plus 1. This thing I plus ai plus 1 is taken in the variable j, and we'll check whether that is less than equal to n. If that is less than equal to n, I'll take minimum of dpi and dpj. Okay, so in dpi I already have I plus 1 plus 1, and dpj is dp of this thing. So this min is taken here. Okay, I hope you understood the transition, how we wrote the transition. This was the base case. Now after this, what would be my final answer? So if my you can understand from the state, my dpi represents for subarray I to n, what's my answer? So my final answer would be for subarray 0 to n, what's my answer? So my dp0 would store the final answer after computing everything. So we can just print our dp0. This would store my final answer for the whole array. Okay, I hope you understood the code what we did. You can also write a recursive code for this dp. Same way in a recursive function, you can write this as a transition and this as the base case. If I is equal to n, then return 0 would be my base case, and inside the recursive function we can write this transition. So I hope you can try that by your own only. So I hope this problem is clear to you. If you look at the time complexity, this taking the input is taking me order of n time. There is n inputs. Okay, and then I'm initializing a dp vector of size n. And so since this is a dp of size n, and the transitions, these transitions are all a simple order of 1 time constant time operations. So this whole transitions is order of 1 constant time, and there are n states in total. So a total of this loop is running order of n times, and then we are printing our answer. So overall order of n and order of n. So my time overall time complexity for this solution is order of n, you can understand. What's my space complexity for this solution? So basically we are taking an array of size n and a dp vector of size n. So order of n, two arrays of n sized. So overall space complexity would also be order of n. So order of n would be well accepted for these constraints of 2 into 10 to the power 5. You can understand. So I hope this problem is clear to you. This was a really nice DP problem where you had to think a little bit differently whether you have what state you have to take. Otherwise it became really simple, because the main observation here was a take not take approach. Whenever you get some problem where you have to either take or not take an element, then a DP approach like comes automatically to your mind. You just need to make sure how you would write the transition, that you have to basically you have to select a state and transition in such a way so that you can basically solve the problem. That was the main thing to understand here. I hope it is clear to you. Thank you very much for watching.